Okay, so in this chapter, we'll talk about work and energy. Okay. So let's say this person pushes this object and does work on this object. So when you do work on an object, what you're doing is you're transferring energy to that object. So work is a means of transferring energy from one object to another object. Okay. Now the total energy you probably know about the conservation of energy. Okay. What does the conservation of energy say? That the total energy of the universe is conserved. Okay, so you cannot create or destroy energy. So whenever you're doing work, all you're doing is moving energy from one object to another. Okay. So everything you do in life from an energy perspective, it's just moving energy from one place to another. Okay. All right, so we will learn about all of that. Kinetic energy is the energy in the motion of an object. Okay. So these are the topics we'll study: kinetic energy, work. We'll see how to calculate the work done when you're applying a force. Okay. So then we'll look at the work kinetic energy theorem and so on. So energy can be transferred to an object by doing work on the object. Okay. So let's say when you're pushing the lawnmower, and when the lawnmower moves, you're doing work on this object, on this, and so the energy of the lawnmower increases, and your energy decreases. So you used a store of energy within you to do work on it, and so you transferred energy from here to there. Okay. So if you do 100 joules of work on the object, 100 joules of energy is transferred to the object. Okay. So you increase its velocity and friction decreases, and then it all gets turned into heat. Okay. So to do work, one needs energy. Okay. So what we do is, as humankind, we are always looking for sources of energy, and right now we're getting 80% of our energy from fossil fuel sources. Then we convert that to electricity, or in general. Why do we convert it into electricity? I'm sorry? It's easier to transport, and so we've adapted all our devices to electrical devices. Okay, so when you transform energy from one type to another, because the other type is more useful. Okay. Energy is a scalar quantity. Yeah.
So does the work equals to the force times distance?
Well, we'll come to that. Yeah, we'll come to that. Yep. Energy is a scalar quantity, okay, associated with the state of the system. What does that mean? Associated with the state of the system. No, its state means its configuration. Okay, so the energy content of my body right now just depends on the state of my body. It doesn't matter, the history doesn't matter, okay, and so on. It just depends on the state of the history matters in the sense that how did you get to this state, okay. Energy can be transformed from one type to another. So you can transfer mechanical energy in the motion, to heat. You can transfer heat to motion, which is what you do in your car. You burn gasoline, and some of that heat gets transferred to the motion of your car, and so. Hey, Christina, can you Can you empty that thing? I don't like the noise. What?
I'll eat it later.
Yep, there you go. You can eat it now, except that. Okay, it can be transformed from one type to another. Okay, you can transform any form of energy to any other form. Some transformations are more efficient than others. So, for instance, mechanical energy to heat, the motion of your car to heat, you can transform 100% of that. The other thing, well, so the motion of your car can be transferred to heat 100%. You also do the other way around in your car. You burn gasoline, produce heat, and try to convert that into motion. That's about 20% efficient. Okay. What happened to the other 80% of the heat? What? It went out your tailpipe. You put $5 of gasoline, you got $1 of motion. So that's why heat is the worst form of energy. Okay. And then, Christina sees a squirrel on the road and she applies brakes. And that thing goes out the window too. All right. So, can be transformed from one type to another and transferred from one object to another. See, this guy, when he pushes, he's transferring energy from him to that. Okay, so you can transform it from one type to another and transfer it from one object to another. How do you transfer energy from one object to another? I'm sorry?
Work.
Very good, my friend. You do work on the object to transfer to them. Yep.
So is sound a form of energy?
Yep. Well, there's energy in sound. Yep. Yep. The total energy of the universe is conserved. Okay. So here are various devices. They are transformers. What do we mean by transformers? They're converting energy from one type to another. Okay. So plants will absorb electromagnetic energy, and via photosynthesis, the process, they'll convert it into chemical energy. You can take chemical energy and oxidize it and convert it into radiant energy. Solar cells convert radiant energy to electrical energy. Light bulbs do the opposite. Electric motors convert electrical energy to mechanical energy. 90% of the world's work is done by electric motors. Yeah. And generators convert mechanical energy into electrical energy. Okay. So here are various devices we use in our lives. Kinetic energy is the energy of motion. So whenever an object is moving, it has kinetic energy, and it is 1/2 mv squared. Okay. You'll also see that that's equal to P is linear momentum. P is linear momentum. It's a vector quantity, mass times velocity. So P square is the dot product of P with itself. Okay. It's the magnitude of the vector square. So the kinetic energy is P squared by 2m. All right, so how do you transfer energy from one object to another? By doing work on the object. Okay. So when the first object does work on the second object, energy is transferred from the first object to the second object. Okay. All right, so now we'll keep it simple. We'll start off with simple stuff. So work done by a constant force. What that means is, as this object is moving, this force will remain constant. Okay. we won't change that force so as the object moves. So the work done by this force on that object, so work done by this guy who's applying the force, is given by that force times displacement times cosine theta. Okay? And that happens to be, if you remember your dot product, it's the dot product of the force vector and the displacement vector. Okay. Now notice a couple of things about this formula. That's the magnitude of the force, that's positive. That's the magnitude of the displacement vector, that's positive. Cosine theta, on the other hand, this guy can be positive, negative, or zero. Okay. So for acute angles, that is positive. For 90 degrees, that's zero. For obtuse angles, that's negative. Okay. So you can do positive work, you can do zero work, or you can do negative work. When you do positive work on an object, you increase its energy. When you do zero work on an object, of course, you don't change its energy. And when you do negative work, you're decreasing the object's energy. So when you stop your car, you're decreasing the energy of the car, so you're doing negative works. When you apply brakes, you're doing negative works. Okay. When you hit the gas, you're increasing its speed, you're doing positive work. Okay. And when its speed is constant, you're doing zero net work. Okay. You still have to have your foot on the gas because there's air drag that you're working against. Okay. All right, what are the units for work? The units for this guy are newtons. The unit for this guy are meters. What are the units for this guy? This is dimensionless. Okay. So whenever you see cosine theta, sine theta, e to the power something, they're all dimensionless quantities. Okay. These are all dimensionless. Okay. So that is dimensionless. Okay. So the units of work are Newton meter. And this combination is given the name Joule in honor of Mr. Joule. Okay. All right, so now this shows you applied this constant force and this object moved like that. The angle between the force and the displacement vector is an acute angle, so you did positive work here. In this case, so for instance, this lady, she's lifting the bag and walking that way. The displacement is horizontal, so zero work was done on this object because theta is 90 degrees. Yeah. And you guys have done this, so here's you apply a force in that direction and the displacement is in this direction. The angle is obtuse and you're doing negative work. Okay, so if you have a runaway cart, you're pulling on the cart and slowing it down. Okay. So work done can be positive, negative, or zero. All right, so what we did was we showed you the formula for the work done when the object was moving in a straight line and the force was constant. Okay. Well, what do you do when the force changes or the object is not moving in a straight line? All right, so let's figure that out. Okay. So this was the formula when the force was constant and the object was moving in a straight line. So now we'll do it where the force is changing and the object is not moving in a straight line. But we'll do it one piece at a time. Okay. What we'll do is, so first we'll make the force change, and then later we'll make a non-straight path. Okay. So first we'll consider where the force is changing, but the object is still moving in a straight line. Okay. All right. Now you guys are all calculus experts. So this is the first thing you learn. If something is changing, break it into small pieces where it's not changing. Okay? So if the force is changing, so there's the force. Okay, the object moved from here to there. What you do is you break this displacement into small displacement, and in this small displacement the force didn't change, and that you know how to calculate. Okay. What was the work done in this leg? This force times dot product with this displacement, or the x component of this force times this displacement. Okay. X component of this force times this displacement, dx. Okay. So you break that up into little pieces. So the work done is the x component times the displacement on that direction. And if the force is changing fast, all you do is break those little pieces into smaller and smaller pieces. So in the limit delta x goes to 0, there's the x component of the force, dx. And in summation is in the limit x delta x goes to 0, the summation becomes an integral. So the work done is that integral. Okay, so what this graph is showing you is the x component of this force. Okay, so you apply this force, the x component of the force at location x is that. Okay. So here is the x component of the force plotted as a function of position. And what is this area? What is this integral? It's the area under the curve. So that is the work done. All right, so what we have generalized is now, if the force changes, that doesn't bother you anymore. All you do is take the x component of the force, okay, or the component of the force along the displacement, plot that, take the integral of that, and that's the work done. Okay. The object is still moving along a straight line. Now let's generalize it to the case when it's not moving in a straight line. And let the force change as well. All right, so we'll do that. There you go. Okay, so now we'll let the object move along any path it chooses. And the force can change any way it wants. Again, you are experts at calculus, so when things are changing, just break this into little steps. How small should be the steps? What you want is in that little step, the force is constant. Okay? The work done in this step, there's the step. The work done in any step is just that, the dot product of the force and the displacement, the infinitesimal displacement. And then just add them all up. That's the total work done. So the work done along any general trajectory is the line integral. Okay. And we won't be doing many line integrals, but you will see you'll see how to do line integrals in Calc 3 classes. Yep. Has anybody seen line integrals? What's that? All right, so what you learn is you learn to parameterize. So here is a physics way of doing it. So the object is here at time t1, t2, t3. So you're giving the path you learned is given as a function of time, the motion of the object. Okay. So what you learn is so. All right, I'll write it down, but don't worry about it too much. Okay, you'll learn to do this in your. Okay. That's the x component of the force, y component of the force, okay, and z component of the force. It'll look complicated, but it's. So F dot dr and remember you are integrating over that, but see, this is a function of x, y, and z, but they're all functions of t. So this will be ultimately can be written as a function of t. Dx will be dx by dt times dt. So you see now this has become an integral over just t, over a single variable, and you know how to do that. Okay. All right. So let me summarize this stuff. Okay, what did we want to do? We wanted to calculate the work done by a force. Okay. If the force was constant and you move the object there, that work done was easy. Okay. Now then you generalized it to the case where the force was changing. Okay, you said no big deal. We'll just calculate the x component of the force. Okay. So, and there was the x component of the force as a function of x. At this location, that was the x component of the force. This location, that was the x component of the force. And the work done was just the area under that curve. Okay. And for a general trajectory, so these two expressions were when the object moved in a straight line. For a general trajectory, the work done was this line integral. Okay. All right. All you did was generalize this expression. Okay. This generalization was for the force changing, and then the next second generalization was the force and trajectory changing. Okay. Okay, so if you're an engineer, you will be dealing with springs the rest of your life. Okay, so let's make sure we understand springs. So here is a spring. What you do is if you stretch the spring will pull you back. So you can attach a mass and then pull on the mass, and the mass will be pulled back. It turns out that the force with which the spring pulls you back is proportional to the stretch. You stretch the spring by amount x, it'll pull you back by kx. The negative sign just tells you if it pulls you in the opposite direction. So if you stretch it this way, the spring pulls you in that direction. If you compress the spring pushes you in this direction. Okay, so if x is negative, negative of negative, the force will be positive. Okay, so the force that the spring exerts is given by that. This fella is called the spring constant. And stiffer the spring, greater K is. Okay. All right, so K tells you how much force you need to apply to stretch the spring 1 meter. Okay. So, for instance, if you apply 1,000, if K is 1,000 Newton per meter, what that would mean is you would have a spring, and if you hang on to the spring, if you hang by the spring, your weight is roughly about 600 newtons, let's say 1,000 newtons. The spring would stretch 1 meter. Okay. Your cars have springs of about 25,000 Newton per meter. Okay. So about 50 people would have to hang on to the spring to stretch it 1 meter. So yeah, cars have in the suspension fairly strong springs. We will do a lab where we'll use springs of spring constant 10 Newton per meter. All you have to hang is 1 kg and it'll stretch 1 meter. Okay. This thing is called the Hooke's law, after Mr. Hooke, who discovered it. Okay. Okay, so you have to be familiar with this thing. You will use this forever and ever. Okay. So here's an example. See, the x component of the force, well, it's only applying a force. The force is dependent on the location, on the position of the object. Okay, so let me attach a mass on this. So here is the equilibrium position, and let's say I stretch the spring like that, and the object moves from here to there, from here to there. So this is your initial position, and the force the spring exerts depends on the position of the object. So now if you want to calculate the work done by the spring on this object as it moves from here to there, this is what you would do. There's the force that the spring exerted that depends on the position, and you integrate from the initial to final position. Well, the integral of that is, so minus k is constant, x squared by 2 and I will so the work done by the spring was that minus that. Okay, let's go back to this diagram. What we have calculated is the work done by the spring on this mass when it went from here to there. The spring force is very special. Here's why. Okay, so the work done, you calculated when it went from here to there. What was the work done if, for that path? What was the work done for that path? The same. What was the work done for this path? See, the work done depends on only something that depends on the final location and the initial location. How many different paths are there for which the work done is the same? An infinite number of paths. Okay. So, when the work done by a force is path independent, the force is called a conservative force. And the work done by such forces, you see, can be calculated very easily. It is a scalar valued function at the final point minus the scalar valued function at the initial point. You don't have to worry about line integrals or anything. So that's why we love these guys. Okay. The work done is very easily calculated. This guy is called the potential energy function. Okay. So, what is the big deal about conservative forces? Work done by them is very easy to calculate. You just take the potential energy function, calculate the difference in the two, and negative of that is the work done. Okay? And there are only three conservative forces that you'll deal with, and only two in this: gravity and spring force. And next semester, it's the electrostatic force. All right. So we will devote an entire chapter to this next chapter or so. Okay. But now you already have learned the next chapter. So the work energy theorem, this is an important theorem. So we'll consider a very simple case. Here's an object, and it's sitting on a frictionless surface, and there are three forces acting on the object. You're pushing on it. There's the force of gravity and the normal force. The normal force is balancing that. So those two cancel. So effectively, this is the only force acting on it. And when you push on it, it of course accelerates. It accelerates and its speed increases. So what was happening when you were pushing on it? You're transferring energy from yourself to this guy. Okay? And since you're doing positive work, this guy's energy is increasing. And what is happening to your energy? It's decreasing. Okay? All right. So the work done can be calculated like so. All right. So F dx, F is m dv by dt. Force is mass times acceleration, and there's the acceleration. Okay. And so using the chain rule, you can say, okay, dv by dt is, let's say we can write v as a function of x, and then x would be a function of t. So this would be the chain rule. Yep. So what we have done is dv by dt is written like so. dv by dt is dv by dx, dx by dt. So you can think of dx canceling, and there's the dv by dt. All right, well, why did we write it like so? Okay, so now what you can do is you can cancel dx, and this is v. So it's v times dv, v times dv. What you have done is you just made a change of variables by doing that. See, this was integrating over x. Now you're integrating over v. Okay, so you made a change of variables. Why did you do that? Well, this is easy to integrate. What is the integral of that? Is it's v squared by 2. So, and you apply it to the initial and final point. So this is 1/2 mv squared minus 1/2 mv squared initial. What was that? That's kinetic energy. So what this theorem says is the work done by all the forces, the net work done on the object. Okay, this guy does one work, this guy does another work, amount of work, this guy does another amount of work. The sum of all the work done, the net work done, is equal to the change in kinetic energy of the object. Okay, and that's the work energy theorem. Okay, so whenever you do work on an object, that shows up as kinetic energy, on the change in kinetic energy. So that's the work energy theorem. Yep. So the net work done is equal to change in kinetic energy of the object. Okay, so this is a concept you want to become familiar with. It's a useful concept. Okay, when you do work, what are you doing? You're transferring energy from one object to another. Okay, and to do work, you're using energy. Okay, so power is the rate at which work is done. Okay, so let's say you do a given amount of work, and if somebody does it faster, then their power is higher. Okay, so power is the rate at which you're doing work, but when you do work, you're consuming energy, so it's also the rate at which you're consuming energy. Okay. The units for power, work or energy is measured in joules, time in seconds. Joules over second is called a watt, after Mr. Watt. Okay. So power is the rate at which you're doing work or the rate at which you're consuming energy. Okay. So you've all heard of a horsepower. A horsepower is 746 watts. Okay. And this came about, a horse back in the day could work for 8 hours in a field at that rate. It could do at 746 watts. Okay. A person, on the other hand, if you're to work in a field, if you want to work 8 hours, you can work at 1/10 of a horsepower. Okay. So now you know back in the old days why they used animals. They could do the work of 10 people. And you don't even have to cook their food. He knows all about it. You were going to bring hay.
Yeah, I got some.
Oh, okay. All right. So power is the rate at which work is done. Okay, so you did this much work in that much time, the rate at which work is done. Okay, work is the dot product of force dotted with R. Okay, now let's say if the force is constant, you can bring that out. And d by dt is dr by dt, but that's the velocity. So power is force dotted with the velocity. Okay. So if the applied force is constant, it's power is force dotted with velocity. And if the force is changing, that's the instantaneous power. Okay. Okay. So maximum power output for humans for various time periods. Okay. So you can work at the rate of 2 horsepower, but you'd only last 6 seconds. Okay. At a rate of 1 horsepower, a human can function for 1 minute. At 0.35 horsepower, half an hour. At 1/10 of a horsepower, you can work a full day. All right, so 1/3 of a horsepower, you can work for about half an hour. This guy crossed the English Channel on a bicycle-powered airplane. Mr. Allen, he crossed the English Channel in about 3 hours, and his power output was a third of a horsepower. So that was quite a feat. Yeah. Imagine all the Tour de France cyclists can do it. What's that?
It's crazy how
Yeah, yeah. Okay, you guys should know some of these terms. So Hoover Dam is a large power plant, and it's this is a watt. It's about a gigawatt. A gigawatt is a billion watt. Okay, what you can do with this is run about 1 million homes. So a large power plant is a gigawatt. Okay. Your home stove is 1200 watts, 12,000 watts. Sunlight falling on 1 square meter. So the average sunlight here is a square meter. This is a meter. So the sunlight falling on 1 square meter, well, this is the Earth, there's the atmosphere. On every square meter here, it's, you want to remember this number, 1400 watts. That's like 1400 watt bulbs falling. And here's an amazing number for you guys. All you have to do is harness 1 part in 15,000 of this to satisfy all of mankind's energy needs. Well, now only half of that reaches the surface of the Earth, but that's okay. So 1 part in 8,000 reaching on the surface of the Earth is all you need to see. Okay. How do you harness that? I'm sorry? Solar cells. Pretty much all your environmental problems are coming from where? Burning fossil fuels. So come back in 100 years, you'll have the cleanest damn air and the cleanest water. There you go. So power is energy over time. Energy is power times time. Watt is a unit of power. Kilowatt is just 1,000 watts. Hour is a unit of time. Okay? So power times time is energy. So this is a unit of energy. This is what you pay your electricity bill by. This costs you about 12 cents. Okay? So 1 kilowatt hour is 1,000 watts. An hour is that many seconds. Okay? So watt times second is a joule. So 1 kilowatt hour is about 4 million joules. Okay. What can you do with this 1 kilowatt hour that costs you about 12 cents? What can you do? You can have a 100 watt bulb burn for 10 hours. Okay. That would make it 1,000 watts for 1 hour. Or yeah, so you can burn 100 watt bulb for 1,000 hours, or you can run your stove for 10 minutes for a tenth of an hour, 6 minutes. Okay. All right. I will briefly talk about global warming, but it's important enough where I'll talk about it next class, whenever that is. Okay? And we'll do problems from chapter 7.